So I'm going to present work of my PhD student Wenpeng Yin. My name is Hinrich Schutz, I'm his advisor, and Sebastian also contributed some ideas to this. So the task we're addressing here is MC test. Given is a story, which I will mostly call a document, a question, and several answer candidates. And the task is to pick the correct answer. MC test's construction requires understanding of the story to solve the task, so it's a very difficult question answering task. Here's an example. I've taken part of the story to make it short. So James is mentioned, then he walked to the fast food restaurant and ordered 15 bags of fries. He didn't pay and instead headed home. The question is, what did James do after he ordered the fries? Answer candidates: went to the grocery store, went home without paying, ate them, made up his mind to be a better turtle. And the correct answer here is went home without paying. And you can see that this is very difficult because you have to do coreference resolution, you have to do lexical matching, went home, headed home, and questions of this type, what happened after something, are quite hard because there are many difficult cases that can occur. Here are the observations that motivated our work. For any given question, most of the document is not relevant. So we want to pay attention only to a few key regions. At least that was our analysis. Relevant key regions vary a lot in size. So we need flexibility in extraction, in extracting either smaller or larger pieces. Relevant key regions can be paraphrases of the answer. So we need abstraction away from words and literal expression to be able to solve this task. And most key regions are contiguous. And so we assume that the answer can be found in one contiguous snippet. That's not true for all of cases in MC test, but we are making this assumption. Dataset statistics: MC test 160, 70 trained, 30 def, 60 test, MC test 500, 300 trained, 50 def, 150 test. And each item here consists of the document, the story, 5 questions, and 4 answer candidates per question. And the answer candidates are given in 2 different forms, as an answer and also as a statement. And this is given, this is part of the data set. There's important related work, which I will come back to, which will be presented at ACL 2016. I will come back to this at the end of the talk. Method, we pursue 2 approaches here. Textual entailment. In that case, the input to the system is a pair of a document and a statement. There has been much prior work on textual entailment. The novelty in this work is that we don't do textual entailment between sentences, but between a document and a statement, which has not been done as often. And we take a deep learning approach here. Our second approach is semantic matching. In that case, the input to the system is the projection, a pair of projection of question, projection of answer, where we look at different projections, including identity. And this is an extension of our work on deep learning for semantic tasks, which is mainly based on semantic matching. And actually, we solve the textual entailment task also by semantic matching. So all of these are actually ultimately based on semantic matching. To be more specific, there are 3 different formalizations of the matching problem we look at. 2 QA matching problems and 1 SD matching problem. In the following, I'm going to use the letters Q, A, S, and D to refer to question, answer, statement, and document. And so the first approach here is QAP, and that means we project both the question and the answer. And in that case, we project the question into a new space and the answer into the same space, and then we match question and answer in that space. And that matching is done with the document as a background. So that's kind of, this is the attention mechanism that we use the document as a background for the projection. In the second approach, QP, we only project the question, and the answer is not projected, otherwise it is the same. And then finally, the textual entailment approach, in which we match the statement with the document. In all of these cases, we match two vectors, and that's simply going to be cosine. And these two vectors, I'm not now going to tell you what the architecture is that computes those two vectors. And those two vectors you see here. So this slide explains how these two vectors that we are matching are computed. So the input to this network is the document, the story, which is a sequence of sentences, and also the query. And the query can either be the question, the answer, or the statement, depending on which configuration of the system we use. And so this is a hierarchical CNN. Hierarchy refers to the fact that here is the word level. Above that, we have the sentence level. So each vector here is a sentence. And above that, we have the snippet level. Each snippet consists of a sequence of several sentences. So each vector here is a representation of a snippet. It's an attention-based approach. And the attention comes here through the query. So the query provides attention, so to speak, on these two different levels. And that attention is used to select sentences and to select snippets. And how many we select is a parameter. In this work, we use 2. So we select 2 sentences here and 2 snippets here. And these two are then combined through one max pooling into one representation of the query that is mediated by the document. And the representations on the different levels are combined through a highway network. So this is then the document-mediated representation of the query, and we also have a representation of the query that is not influenced by the document. And as I said, these two vectors there are then compared. I'm going to skip that because I don't have time for it. Experiment. So our objective function is to minimize ranking loss. For textual entailment, this looks like this. Remember, in textual entailment, the input is a document and statement. We have a vector for the document and a vector for the statement. And so what we're trying to do here is we're trying to rank the cosine of the document with the correct statement higher than the cosine of the document with incorrect statements separated by a margin. And the same for question answering, for the question answer formulation. S here is cosine, and we use Adagrad 50-dimensional glove vectors fixed in training. We use 2 simple baselines here. One is add. That's simply the representation of question answer as the sum of the embeddings of the words. And we compute then the cosine between, for example, question and answer. And add proj, that's the same as add first. And then we replace each of question and answer with the most similar sentence from the document. I'm saying this here for question and answer, but it's actually the same for document statement. That's, yeah. And then we compute the cosine of the 2 sentences that we have selected that way. Notice that add does not consider the document, so it's a very simple baseline, but add proj does. We also compare to 2 important papers from the literature, the Neural Reasoner by Peng et al. I don't have time to explain that in detail, but it's a re-implementation, so please take our numbers with a grain of salt. It's not supposed to say anything negative about this great work. It's not necessarily the best architecture, of course, for this task, because the order of the facts is not taken into account here, because for this particular task that the architecture was designed for, the order doesn't matter. But here, in our case, the order does matter. And the second prior work we consider is the attention reader. Again, this is a re-implementation, and it's actually on the sentence level, so this one you have to take with a really big grain of salt. So summary of systems, we compare our work to simple baselines, add proj, and state-of-the-art deep learning, the Neural Reasoner, and the attention reader. Here are the results. So what you see here, results on MC test 160, on MC test 500. Metrics are accuracy and NDCG. And then there's evaluation on those questions that can be answered based on a single sentence and where you need multiple sentences, and this is the combined evaluation. And then comparison here is the two simple baselines, the attention reader, the neural reasoner, in parentheses because these are re-implementations, and then our three methods here. And so the good news is that the textual entailment system seems to be beating all of this other work. And if we look at one column here, then in detail, then you see that the distance to the prior work is pretty large, and all of our architectures seem to be doing pretty well for this task. We can visualize the attention. That's what we've done here. So this is a different story, and here the question is, what did Grandpa answer? Why did Grandpa answer the door? And on the left, what you see is single sentence attention weights. So that corresponds to the attention weights on the first level of the hierarchy. And here we have sentence pair attention weights. So these are the attention weights on the next layer of the hierarchy, the larger chunks, the snippets. And so if you look, for example, at this sentence here, he could have taken a ride to Grandpa's house. Then on a single sentence level, that's recognized as being relevant. But then if you look at the larger context, the network realizes it's not relevant and the attention weight is attenuated, whereas that is not the case for the part of the story that is actually gives you the answer. Error analysis, the limitations of the HABCNN, counting, how many rooms are there in the house, something like that this architecture cannot really do. Temporal reasoning, in which year was he born? If the number is not given directly in the text and you need some kind of temporal calculus to come up with the year, then that's not something we can do. Causal reasoning is really hard. Why did the accident happen? And in general, complex inference is difficult. And so maybe these are phenomena that are difficult to handle with distributed representations combined with convolution and pooling, even if you add attention as we do here. Performance of neural models versus non-neural models. So I showed you that HABCNN was doing pretty well compared to prior neural work, but of course there's also a lot of non-neural work. I've put up a few good examples here, papers that are usually feature intensive. I mean, they just use we now know that this is the new traditional way of doing NLP. So these are traditional quote unquote NLP papers. So our numbers are below the state of the art in non-neural question answering. Possible reasons for that are the problems I just talked about: counting, temporal causal reasoning, complex inference. Small data set. As you saw, these are very small data sets, so deep learning usually requires large training sets, and that's probably the biggest reason. Also, we do here a kind of purpose selection of parts of the document, and in standard CNN pooling, there's a per dim selection, and we're doing some follow-up work on this, where it looks like that this purpose decision in this architecture was a bad idea. And maybe traditional stat NLP is just the right approach for this type of task. So maybe this is actually not every problem needs to be solved with deep learning. As I said in the beginning, so this is the ACL 2016 paper by Trishla et al., which has some similarities, but gets much better numbers. So I want to compare our work to their work. Possible reasons why they are doing much better is, one is they have a more fine-grained hierarchy. So we only have two levels here, the level of sentence and the level of snippets, but they have two more levels, and they show that that is actually critical for performance. Training wheels, they make much better use of the training data by doing some clever things with the training data. We just did this pretty straightforward training directly on the training set. And they seem to have fewer parameters. So for a small data set, that's of course good if you have fewer parameters. And the multitask part that I didn't talk about in our architecture actually seems to hurt performance. So we thought it was a good idea, but it doesn't look like it is. Trish et al. Also use complex linguistic features. So that could also be a reason that they are doing much better. But if you look at the ablation study they did, then maybe that actually isn't the main reason for their good performance. Summary questions. This is the first deep learning work on MC-test. So we published this about 6 weeks before. We put it on arXiv 6 weeks before Trish et al. One important question here is attention important for solving QA using deep learning? I think it is. But of course, the question is, Trish et al. Don't use attention, at least not directly. So I think it's an interesting question to ask. We seem to be doing better than AR and NER. We have fewer parameters than this prior work, so that may be one reason. And for this task, MC-test extraction is key of contiguous sentences. And so maybe CNN plus pooling is actually the best way of doing that as opposed to using an RNN. And hierarchical abstraction is key over large pieces. Again, a stacked CNN plus pooling architecture might be the right way to do that in deep learning. Deep learning is below the state of the art on MC-test. And as far as I know, this is also true for the Trish et al. Paper at ACL. Why is that? Maybe because the training set is too small here, and maybe deep learning is not the right method for this data set. Our code is online, and we are grateful for the support of DFG for this work. That's it.
Actually, I have two questions. The first one is actually because neural reasoning is all about the reasoning, right? How you try to able data set compared to, using your model called the Babel data set.
The baby data set?
Yeah.
No. I guess I personally have some of the concerns that were voiced this morning about this data set. Although I was very happy to see that now it's being extended to real movie data. So that's why we haven't focused on it that much. But that would be a very interesting experiment to see.
Your model actually something like the instruction and retrieval, but in Babel it's something like reasoning, more like reasoning. Another thing actually, I noticed that so basically a little bit confused me. So there is pooling. Actually, you're using attention with pooling. It's kind of attention-based pooling, or you do pooling then do attention.
This is, so basically the origin of this architecture is that Wen Peng tried many different things, and this seemed to be working best. Where is it again? It's a combination of pooling and attention. So the selection of these vectors, that's attention, but then several vectors are selected and they are combined by one max pooling. Okay.
Another thing actually, a very tiny part. You use the embedding, but embedding size is only 50.
Yeah. Because the intuition behind that is that at the time when this paper the research was done, we had not yet purchased GPUs and
Yeah. Just a comment about the baby dataset and the movie QA. So we also made some other datasets. So in particular, there's one called the Children's Book Test, which is based on like Project Gutenberg books, and kind of looks a bit like the DeepMind QA-CNN sort of task. Kids really like hide words from sentences. And I don't know if you know about that, because we sort of see that as our bigger dataset version of MC-test, right? It's like children's book, but there's a lot more data for training. So you could also try on this one, which several people now have published results on.
And that's called what? Children's
Book Test, CBT.
CBT, okay. Yeah. Thank you. We will look at that.
Hi, I'm the author of the Neural Reader.
Very good paper. Congratulations.
Yeah, I'm glad it's still like one of the best in the competitive models. So to argue for that model, it is really designed for the particular architecture of it is nonlinear interaction between query and facts, and also just layer by layer of processing. So it's sort of not a super for that kind of task because one, it has too many parameters, as mentioned, and two, it's not so good for this kind of expression task. So yeah, you mentioned it.
Right, but I mean, sometimes you make assumptions about a problem. Like, I mean, so I guess the main thing here is that, for example, the order is not important.
Well, there are two coding strategies. One is the implemented one is actually ignores the temporal structure, it just uses coding. And there are also, I mean, I've mentioned in the paper that you could also do some kind of RN over this general.
Some kind of RNN.
Yeah. You could have a temporal sensitive kind of coding over that. But I didn't do that. Maybe I just mentioned that.
Okay.
I guess that's not really the reason it didn't work that well. I guess the main reason is that it needs, I think it needs over 2,000, I think 2,000 example to work with.
Okay.
Not too many parameters.
We have to stop here. Let's thank the speaker.
Thank you.